Caroline Smith. It is April 30th, 2020, and this is my senior project presentation for my free space finder. I am a computer engineering major. Just get us started there. So, what is the point of the free space finder? Or FSF? What am I actually trying to solve? Well, the big question in general that I am trying to answer is, where am I supposed to park? Now, you may say that doesn't really sound like that big of a problem to try and solve. It's not really worth a senior project on it. But NRICS, a company that focuses in statistics regarding driving and drivers, actually has some stats on that to show that this is a bigger problem than you might initially think it is. For instance, 61% of American drivers have reported stress specifically related to trying to find a parking space. 42% that were interviewed said that they have missed an appointment from an inability to find a parking space. 34% abandoned a trip entirely because they could not find a parking space, so they were not going and they turned around and went back home. 23% experienced some kind of road rage related to parking. And in addition, there are 5,300 universities. Now, you might think that's a little unrelated to the other stats that I've been giving, but actually, one of the biggest problems reported from college students, especially those that live off campus, which is the majority of college students in America, say that one of the biggest stresses in their life outside of academics is trying to find a parking space to get to classes. Specifically, that is 19.9 million of those college students at those 5,300 universities. So I would say there's definitely some kind of market there, some kind of thing that we can try and solve. Now, as this is a kind of a problem, I am not the very first person that has tried to solve it. There have been multiple historic attempts. The one that you would probably be most familiar with right off would be parking garages. Now, there's multiple different ways that parking garages keep track of how many people are parked inside of them. One of the more common ways is to use a big metal coil underneath that magnetically detects a car, and it can tell which direction that it is going, using two metal coils, which one it hits first. So that's one way, but that only tells you how many parking spaces there are total. You don't know if it's on the 5th floor or the 1st floor or anything like that. So that can still lead to some stress. You're constantly having to circle. You're trying to peek between cars. Is that a parking space? No, it's just that there's a motorcycle in it who parked all the way in the top. So there are different ways that parking garages use those, but in general, they're just telling how many cars are in a space. More similar to my own project is the magnetic ground sensor. This is used in some big cities. I know that Barcelona has used something like this. Some big cities in California, like San Francisco, have tried to use this, where you put a very large, or put a sensor in the ground, and it tells when a car is on top of it, and it's connected to some cloud. And theirs tend to work really well. They have a 95% accuracy rate as their standard, but they also cost $200 to $400 per unit. So that's really a lot higher than most places like a college campus would be able to afford for every single parking space. So, back to my project. The main design objectives that I would have, the things we're trying to achieve, besides just detecting a car, obviously, while solving this problem, is that we would like it to be less expensive than that. As I said, the general group I'm trying to reach would be something like universities or small companies that can't afford have the same budget as some giant city. So we want it to be less expensive than that. I wanted my device to be universally installable. Parking garage stuff works great if you can mount it overhead, but if I'm at Walmart and Walmart's trying to help me out with this, they might not have one over every parking space. And I also wanted it to be really accurate. If you don't trust that the device is actually telling you correctly, then you're going to be circling trying to find a closer parking space. If I'm running late and it says my best one is in the 10th row, but I don't know if it's right, I'm going to be testing it out, and that's going to totally defeat the entire purpose of the project. So getting into more specifics for those, how are we going to measure that? I'd like it to be less than $200. As I said, Urbiatica's, that's the cheapest about one that I could find, and that was $200. So if I could be less than that, I'm saving money. And it should be able to be installed with or without a curb, any kind of overhead hang, pavement, or Wi-Fi connection. Because if you're needing those, it's not universally installable, and lots of parking lots just don't have those. And lastly, I would like for it to be at least 95% accurate. As I mentioned, that is the current industry standard. Our specific goal for this project did end up being a little lower than that, with an A grade being just above a 90, but I would really wanted it to be there. And as far as battery life goes, I really wanted this to be able to last 30 days, because especially if you're a small company, you are not going to want to be going around and recharging these every day. That's just going to be wasting a lot of time. It's probably not going to be worth your time. So that was one of my goals going into this. Last one, shorter than 2.5 inches, because if you're trying to put this in pavement or in ground, I didn't want them to have to be digging super deep trying to get into it. So my goal was for it to be shorter than that. So with all those things in mind, this is what my actual design is, the actual thing that I tried to build. I know that a lot of the words on here are too small to actually read right now. If I was giving this PowerPoint, it might be a little bigger, but I will be sending these slides in to make it a little easier to read. But this is just the general layout of the hardware of the device. So we're going to have a printed circuit board that's containing all the components. It's going to be powered by the battery recommended by our microcontroller. The microcontroller is an Arduino Maker 1010 with Wi-Fi enabled that also comes with a Bluetooth connection. The main way it's going to be communicating is by Bluetooth. One of the main reasons for that, you don't need a Wi-Fi connection. It can work anywhere. You might ask why specifically Bluetooth and not something like a radio wave. And the main reason is the radio waves ended up being a really complicated interface to go through, and we decided for the scope of this project, Bluetooth would probably be easier to work with. So if this was fully expanded, that'd probably be something you'd want to switch over, but for the purpose of this project, just using Bluetooth. But this is a device that uses double-checking sensors, I'll get more into that in just a minute, between a compass and an IR sensor that tells whether or not a car is on top of it and communicates by Bluetooth to a server, client device, specifically your cell phone, whether a particular parking space is taken. It is housed in a device that looks like this. You can see there's different mounts in there for all of this. I'll explain this a bit more in the actual picture of the device. But this was the plan going into it for what this was going to look like. And this is what it actually did look like. So as I said, I'm going to explain a bit more how it works. But this is the infrared sensor. This is the Arduino microcontroller. This is the compass / magnetometer. And this is the housing. The only thing missing in this picture is the top plate. There is an acrylic plate that screws onto the top, but that really obscures the part, so I didn't have it on for this picture. But if the full design, that would be in there. So how does this design actually meet the criteria that we're talking about? First off, it detects the car, communicates this is where a car is. So in the grand scope of things, this is more of a prototype. The idea would be that you would put one of these in every parking space, and then you would use a database to say which ones were open, and you would be able to then say, okay, which one of those is closest to the opening of the parking lot. But again, I'm just trying to make the device that senses the car, but that would be in general, okay, I'm pulling up to a parking lot, this is my closest space. So that's how that actually solves the problem that we've been talking about. So the way that this works is it uses a double checking sensor system. So the IR sensor is constantly looking up, well, not constantly, it only turns on every 5 minutes, but it's looking up and saying, hey, where is there a car? Is there anything on top of me? Is there anything within 4 feet, specifically? And if it sees something, then it activates the compass. The compass is reading the magnetic field in the X, Y, and Z axes. And if something very large and metal were to come on top of it, that would affect the magnetic field. Now, it's not able to tell you how big the metal object is. We're not trying to tell that, but it does say something big that is messing with the magnetic field is on top of me. And if it sees that, and there's something on top of it, that most likely means there's a car. So it communicates, handles that data, communicates that, and then sends out a Bluetooth signal using the built-in Bluetooth low energy capabilities of the microcontroller, which are then read through the NRF Connect app, which was mentioned in the last slide. So that's how it actually works. That's how it solves the problem. Again, that's the IR and magnetic sensor. And my total cost for all of this was $116. That was a little lower actually than I was estimating. And that's not to mention that if this was mass produced, it could be distinctly cheaper. If I was making this in a factory, I would not be using an Arduino microcontroller. I would be able to use something that only does exactly what I need it to do, which could afford to be a lot cheaper. And also the PCB would be more in the realm of cents, less than $1, as opposed to the $33 that I spent on it. So I would say that this is very easily able to market price less than $150, perhaps significantly lower, depending on how much that chip was going to cost. But I would definitely say it was less than $200. So going into those goals, aside from the cost that I mentioned at the beginning of this talk, the accuracy. As I said before, I wanted this to be at least 90, but I really wanted it to be more than 95. And the way we tested this was we set it out on a concrete parking lot, and we drove a variety of cars over it in a variety of different situations. So sometimes there was a car next to it. Does it think there's a car? There's a car on it. Does it see the car? There's two cars on either side of it. Does it think there's a car? And different situations like that. A car recently left. Does it think there's a car? And we did that repeatedly. We tried to try most of those situations multiple different times to make sure that we weren't just measuring a fluke. And the results, I am very happy to say, were 100% accurate, almost. I say almost because one, saying 100% accuracy is kind of sketchy, but two, technically, we were able one time out of the 44 tests that we conducted to make it say there was a car when there was not, but that was only when we had a car on either side within a foot of it and someone manually triggered the infrared sensor. And if that's the case, you can't park there anyway. So I would still qualify that as passing all the tests. But if we don't quite call that, then it's 97.73% accurate. As far as the battery life, this was definitely something that was a little bit of a disappointment going through this project, because very late in we realized that because of the way the Arduino was made, one of the resistors was missing. So we were not able to use the built-in voltage amplifier, which, suffice to say, there wasn't enough power going to the Bluetooth. It couldn't run unless it was connected to 5 volts. The company recommended a 3.7 volt battery, so that's what I had. So the device only actually works if it's plugged into a laptop by USB, which kind of defeats the whole purpose of it being universally installable. However, because this did end up being a lot different than I planned to be. So the way we tested it instead was we ran the device without it trying to tell us if there was a car, and just let it die. And then I included battery saving functionality, and then did the same thing, and we compared how long it took it to die in those situations. And that was to show if we were to run this correctly with the battery saving functionality, it would last longer, though it's hard to say exactly how long. So on its own, it lasted for 16 and a half hours. When I added in the battery saving functionality, it lasted about 30. The exact time isn't known, but it was definitely significantly longer than 16.5 hours. So the improvement suggestions that I would have for this, I did want to mention it was shorter. It was exactly 2.5 inches, so it fit within that size requirement as well. Number one improvement, what I just mentioned, getting the Bluetooth battery problem fixed. There are multiple ways you could do this. One would be to buy a separate Bluetooth system to attach to the Arduino. That'd be a little frustrating since it's supposed to be built in, and I paid more for the one that's supposed to have Bluetooth, but that is one way you could fix this. Another would be to go in and try and add that resistor as a surface mount, which is a little bit beyond the scope of this project, we decided, but that would be the number one way to improve the design as it is right now. The other would be, as I mentioned, the general battery life. We got it to last about 30 hours. You could include some transistors to cut power to the sensors entirely. There's a lot of things you can do to make that battery life a little bit longer. And lastly, again, battery-based. That's why I put this guy in there. All of these are battery-based. The battery placement, as you can see, this is the device itself. This is the PCB circuit. The battery goes underneath the circuit, which is only sitting about 0.75 inches off the bottom. Which works, the battery will fit under there, but I didn't really think when I was designing this about the fact that you'll need to get the battery out. And it can be really, really hard to wiggle it out without unscrewing the whole PCB, which would be a real hassle. So that'd be a number one thing I do, is probably to make that a little longer so you could slide the battery on out. Alright, so in conclusion, what would I consider the general successes of this project? For one, I was incredibly happy with the accuracy that I was able to get. The fact that it would well surpass the 90% goal or even the 95 goal, even when some of the tests included triggering the IR sensor when a car was there, but it would not detect it if the car wasn't right on top of it. That was really exciting for me. And the other was general PCB and box design. The circuit board, I'd never done anything like that for anything before, so the fact that it worked out well enough once it was soldered on that it was actually functional was something big that I learned from this, and I would consider one of the main successes that those worked out. As far as general lessons that I would say that I learned, learned how to use a whole lot of software and machinery. I had never used hardly any of the power tools in the engineering shop. I had never designed a PCB board before using EagleCAD, so that was really cool. Getting to work with the interfaces for these sensors, learning how to do that was also really cool. Designing an entire system and making it interconnect. I've done small pieces of things like this, like an assignment where maybe I would want the sensor to talk to me, but having to take in that sensor information, have it do this, once it does this, communicate it. Just getting to design that was something I got to do that I've never done before, that I learned a lot from. I also mainly learned that everything is harder than it sounds like it is. I really thought the sensors were going to be much more of a plug and go kind of thing, and they weren't. It took a lot of time for me to get those sensors to work and calibrate them and know how to do stuff with them. Even the Bluetooth, I chose that specifically so it'd be easier to interface with, and that ended up being pretty hard. So that was exciting to get that to work, but that was one main thing that I learned. As far as general advice for the engineers next year coming into this class, communicate early and often with your advisors about what their specific requirements are, what they specifically want you to do, because their ideas may be a little bit different than what you're thinking of. You may think they want more or less from you, and there's no need to be losing points or overworking yourself when it's just not necessary. Don't be afraid to Google how to do things. The point of this is to reach beyond what you already knew, and so no one's taught you in a class how to do a lot of what you're going to be doing. So Google things. Don't just look for examples of people that have already done it, though. Look for data sheets. Look for really hard data from the company of how to use this. And lastly, I would say to challenge yourself with your project, but not too awful much. Like I said, everything's going to be harder than you think it is. So if you're in the beginning of this and you're thinking, yeah, this is going to be a really huge project, you probably want to work on your scope a little. You can do something really cool. You can make something work without it being, Elon Musk, the next thing going to Mars. So I just want to close by saying a big thank you to a lot of professors. Mr. Woodham really helped me out with this box design. He was incredibly helpful with getting everything 3D printed and some other advice on the layout. Dr. McGarry helped me out a lot with designing that PCB. Like I said, I've never done that before, and even some with the soldering help. And especially Dr. Lovegrove, my advisor for this project, was incredibly helpful in finding information, choosing the right sensors, choosing the right board, making a lot of really helpful decisions, helping me decide on that scope, really narrowed me down from the beginning of the project what I thought I was going to be doing. And lastly, I want to say thank you to Mr. Seth Dargy, who helped me design my logo that you saw at the beginning of this presentation.